Okay, we are in section 3.8, derivatives of inverse functions and logarithms. We're going to be heavy on the logarithms and slightly with fewer examples on the inverse. But we do want to consider this, and we're going to talk about what an inverse is. An inverse is known as the undoing of f of x in terms of x, where f of x then becomes the interchanged values of x and y and solve for the new y. That's how I was taught. The book uses a fascinating aspect, and I'll discuss that with you as we go on. So we're going to focus on the fact that we have a proof of f inverse of x is x. Therefore, f inverse of f of x is also x. So what we're saying here is that the inverse creates this y equals x notation or focal point, if you will. It divides both of the occurrences in that regard. So we know, find an inverse of a function first, rewrite as y equals place of that f of x. That's the first step, make it y equals. And the way I taught it when I was teaching this in algebra is the fact that we interchange the x and y values and we solve that interchange for y. But here's the last and most important step. We have to again rewrite that y, because it's an inverse, as f inverse of x. This is very critical. And so as we go further, we'll be talking about that. All right. So here is our rule. And what this rule says, that if we want the prime of f inverse, we use the b. In other words, we have some ordered pair AB. And because all ordered pairs of an inverse function to be a function are BA. In other words, we flip what they are for the inverse function. So it says here, if we have a function, an inverse function, and we take a derivative, then we use the b value and know it's 1 over that derivative. So here we have it, that we can definitely use, and that's what we're getting at. Can use derivative of the function as f prime of a, write the reciprocal value. Or d dx of f inverse of x. And that's what's listed here, that we can do it in this fashion. All right, so here's a proof that was in the book, and it's short and so cute. It says the function of the inverse function is x, because we know the composite feature of an inverse times the function is, the composition of the inverse into the function will give us x. Then if we take the derivative of both sides, we get 1 for x, and then we get the f prime of the inverse as a derivative of that inverse. Well, then if we divide by that, then we can see what we were talking about that derivative. So we're going to do the long form of this guy. And notice that it says a is 1/3. So let's talk about finding out what f of a equals in terms of y. All right, so we want f of 1/3. So I'm going to have 1/3 plus 9 divided by 1 minus 2 times 1/3. I'm going to do the math. And this is going to be 28 thirds over, and this is 1 minus 2/3, which is, 2/3 is a third. This is a complex fraction. Keep, change, flip. So we're going to have f of 1/3 is equivalent to 28 over 3 times 3 over 1. Well, those cancel, so we have 28. So our ordered pair is 1/3 and 28 for the original f of x. That's important to know. So we have that calculated. Now we want the inverse of the function. Okay. Now we're going to do it two ways, and the reason for that is to let you know, if you do read the book, this is how they do it. So in the book, we're going to write our function. And then solve for x. So I'm going to cross multiply. And remember, I'm solving for x, so I'm going to have y minus the 2xy equals to x plus 9. All right, so I'm going to put all the x's on the right and all of the y's and numbers on the left. So I'm going to have y minus 9, because I'm going to subtract the 9, equals x plus 2xy. Okay, so now I'm going to factor out an x, because I'm solving for x. 1 plus 2x. And that leaves me, 2y, sorry about that. Oh my. Oops, way too big. All right, so now I'm going to divide both sides by that 1 plus 2y. So I'll have x. Now we want the inverse because this is for the inverse of the function in terms of the output being x. So that we would rewrite this and exchange y for x. This is our inverse. And that's how the book did it. Now, the way I taught it, everyone, I thought this was fantastic. I'd never thought of it like that. Okay, we do the y equals that x plus 9 over 1 minus 2x. And then I'm going to cross multiply. I'm sorry, interchange first. Sorry, I'm doing it like the book. X equals y plus 9 over 1 minus 2y. Where x is, I entered y. So now I'm going to solve for y, do a cross multiply. I'm going to do distributive property. I'm going to subtract the 4 and add that. So because I need the y's on one side. This time I'm factoring out the y. I'm going to divide both sides by that factor. Sorry about that. So now I'm going to rewrite the y as f inverse. It's a 9. I read it as a 4, and I'm sorry, all the way through. I should have made my 9 prettier. Or maybe my ink's too thick. I don't know. So either way, we get the same information. Now this is where we're going to be looking at proving proof that they showed us. They want us to evaluate derivative of the original function. So we know that f of x was, and oh, we needed to look also at the similarity of what we had. It's x plus 9, and here it's x minus 9. It's 1 minus 2x, and here it is 1 plus 2x. So that's kind of an interesting output of an inverse function. All right, now that I did that. So our function is x plus 9 over 1 minus 2x. This is our original function. So we want df dx, which is a quotient rule. The derivative of x plus 9 is 1 times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Right. So we're going to now do a little bit math. Positive all over the bottom squared. All right, so I'm going to take care of additive inverses. And And that's going to leave me as the derivative 19 over 1 minus 2x squared. Now, all they asked for was a derivative. Now I'm going to do evaluate the inverse. So that one is the one we just did. Sure, I see the 9. So we're going to interchange. We're going to first put in our derivative. Again, quotient rule. 1, parenthesis, the bottom, minus the derivative of the bottom, which is a positive 2, times the top. Sorry about that. So I'm going to clean this up. And I'm going to simplify this way on the side. And I'm going to have additive inverses. Oh, and that's a minus 18. That's a minus. I'm sorry. Dismissed. See what I did? Oh, I miswrote it. It's a minus. Careless. Don't be careless like your instructor. And we're going to have 19 over 1 plus 2x squared. Okay, so we can see that they're very similar except for the plus and minus. So now they want us to take the derivative as x equals f of a. In other words, we want b because we're talking about the inverse, to prove that it is the inverse at the derivative at a. So let's do that. Okay, so let's do this one in terms of a equals 1/3. This is going to be 1 minus 2/3. I'm going to go this side because I'm going to run out of room, and I'm sorry about that. I don't think I wrote large, but you can see my math. 19 over, this is going to be 1/9. Well, this is a complex fraction, so it's going to be 19 times the 9. All right, I didn't put my calculator out. Sorry. There it comes. Okay. So I'm going to have the 19 times the 9. I get 171. So we're going to do the one for this guy at 28. And it's very pretty how they write that. Notice how they wrote it. The derivative of the inverse over dx and a bar, and on the bottom they put that. So we're going to put the b28. So here we go. And that's going to give us 19 over 1 plus 2 times the 28. Okay, and this whole thing is squared. This is 56, so that's going to make it 57 squared. All right, let's see what we got here on a calculator. I have 19 divided by 50, what did I say, 57? Okay, yes, squared. All right, now that's an ugly thing, so we're going to hit our math, frac, and enter. Oh my goodness, look at that. How about that? So we can see that it is the reciprocal, 1 over 71. So we've proven this. We said that if we take the reciprocal of df dx, the reciprocal, then we're going to have f in d df inverse of dx. And that's true. We just proved it. All right. Now we have this consideration. Let f of x equal a polynomial. Oh, great. I was tired of the quotient rule. 7x cubed minus 13x squared minus 2, where x has to be greater than 1.5. Find the value of the derivative of the inverse function of x at the point x equals 70 f of 3. So we know our ordered pair is 3 and 70 for f of x. F of x point is 3 and 70, and they want us to find the derivative. So we're going to do f prime of x is 21x squared minus 26x plus 0. Now we want it for the 3, f prime of 3. I'm going to use my handy-dandy calculator. 21 times 9 minus 26 times the 3. Therefore, f inverse f dx of f inverse is going to be 1 over 111. Right, using the rule. Right. Well, here's another aspect that I thought was really cool. And just a little thought, not anything major. Let me make it smaller so that I typed in short print. All right. Suppose that a differentiable function y equals f of x has an inverse. And that means that we have that dividing line, dash line, y equals x in between those inverses. And that the graph of f passes through the point f. Okay, so we have f of x point is 5, 6. And it has a slope. So this is our slope, m equals 1/5 at that point. Find the value of f inverse at x equals 6. Well, x equals 6 is this. And if the function, if f of x, f prime of x is 1/5, then what is x of f inverse of x? It would be the what? Reciprocal. So it would be 5. Pretty cool, right? All right. Now, here is logarithms. And usually when we talk about logarithms, they're either, they are two kinds. We have log of base of product was an exponent, or we have natural log, which is ln of x. So we're going to be doing both, but mainly what we do in calculus is this one. And this one we have to know forever. And that is that the derivative of d to the x of natural log x is 1 over x. And on the logarithms, we'll look at that when I get to them. All right. So here we have that concept. So let's look at this one. They said, find the derivative of y with respect to x. So we want dy dx. The natural log is going to be 1 over 13x. And then we're going to do du, because there's a number in front of x, which is 13, plus the 2. We're going to clean it up. So I'm going to have dy dx equals, well, those cancel, 1 over x plus the 2. There it is. Okay. Well, let's do another one. Hey, now here we have an x in the denominator. That's going to be interesting. Heck yeah. So we're going to have the dy dx equals 1 over that times the derivative of 1 over x. So that would make it negative 6 over x squared. Now we're going to clean up this mess. Y dx, that's a reciprocal value. We're going to have x over 6 times that negative 6 over x squared. And we're still going to clean it up. Y dx equals, and we're going to cancel the 1x here and the 6's. And that leaves me with a negative 1 over x. I find that totally fascinating. Now, remember on this guy right here, it is just a multiplier. But here we have the chain rule. So let's see what happens here. So we want dy dx, and we're going to have 10. I'm going to put a bracket. You don't have to, but I just want to make sure I'm confident of what I'm doing. 1 over sine x, and then we need the 1 over u du, so that would make it cosine x. Is everybody comfortable with that? All right. So when I do the math on this guy, I'm going to have dy dx as 10 cosine x sine x. Well, that gives me cotangent x. Always be good about knowing what that is, which is a lot easier to work with as you go further in calculus. Job. Oh, wow. Here we go. We have chain rule and product rule. Good fun. Here we go. So we do the outside, then the inside. Outside, and then the inside. So I'm going to have dy dx equals 5. And I'm going to go slow. X to the 6 ln x to the, this is a power rule, so it's going to be to the 4th. Now I'm going to do the product rule with inside. So here I go. Now it's the inside. I'm going to do a bracket because it's a product rule. I'm going to take the first term because it's easy. 6 x to the what? 5th. That's right. And the ln x comes along for the ride. Plus, I'm going to have the first term. And then I'm going to take the derivative of the second. 1 over x. All right. I'm going to clean that mess up as best I can. Trying not to forget all of the things that we have going. So this guy is good. But this guy is we're gonna take away 1. Simplify it. All right. So now we have a distributive property. Now, if you want to do the 5 first into this guy and then do the rest, that's quite all right, because that's what I'm going to do. And now this will give me 30 x to the 5th ln of x plus 5 x to the 5th. Now, at this point, this is pretty good. If you want to go further, by all means, go ahead and distribute again. And I think I did that in my practice before I got ready to do the video. So in this case, I would have 30 x to the, oh, wait, sorry. I have to do the inside. I have to do this guy. Sorry. I did do it. X to the 24, power on a power you multiply, ln x to the 4th. And now I have that mess. I don't need that. There it is. Almost made a mistake. Always good days. Here we go. Now I can finish it up. Okay, so x to the 24 plus x to the 5 is x to the 29th ln x to the 4th. X to the 24 times 5, x to the 5 is 5 x to the 29 ln of x. Oops, That's an ln of x to the 5. Sorry about that. I'll go back. All right. And there it is. That's it. Hey, pretty fascinating. A little bit math, that's all. A little bit math. Okay, on this one, they're telling us take the derivative of this function. And inside we have the quotient rule. All right. So we're going to say d dx equals 1 over this mess. And now we're going to do the quotient rule for that argument. I'll flip this over in the second movement. So I'm going to have a 5 times the bottom minus the derivative of the bottom times the top, all over the bottom squared. Okay, I want to flip this guy now. Now I'm going to do some math up here. Right, I'm going to look for additive inverses. It's kind of like a pattern, isn't it? I know. If you can see that, that's awesome. I'm going to have a negative 40. That's what I have on the top. 5x minus 4 squared. All right. I'm going to look for common factors. This guy takes care of one of those. And that leaves me with what we want. Negative 40. And this is the difference of perfect squares. So this is going to be 25x squared minus the 16. And we're done. All right. Okay. This one talks about a logarithm, and it's very involved, and I think I probably removed these because you'd have to take the natural log on both sides, and that would be on the top and the bottom, and it's very, very ugly because I picked a bad one. I mean, I can do it, but we're going to omit this one. And we're going to go to this one. Now, this one is a rule, and I didn't put it on my notes, so I'm going to write that rule for you. And again, you're going to write it on your notes, on your formula sheets, to make sure that when you take this test, you can review this. All right. So the rule is d dx of a log of base a of some value, unknown value, is, again, a reciprocal value, 1 over x log of that number. And now we're going to add the du if the argument of x has a variable or exponent. All right. So this is our derivative rule. All right, so here we go. Y dx equals, now we're going to take the derivative here. It's going to be 1 over x log of 3. It's a change of base is what it is. It's a change of base. And if you can see that if we take the derivative of x, it's 1 over x. And if we change it, we'd have to multiply by the log of 3 because that's the base we're using. And in this case, we don't have any exponent on x, so then we're going to put plus. Now on this one we do. And here we go. We're going to have 1 over x to the 8 log of 3. And then we have the du on that guy, which is 8x to the 7. There you go. So we have the dy dx is equal to 1 over x log 3 plus, and here we're going to cancel, let's cancel that and make it x to the 1. So we're going to have 8 in the numerator, x log 3. Okay, and this is the answer. All right, folks, now you can do the homework. I have omitted the ones that take a very long time to do. Not that you can't do them, but it's just not, I'm not going to spend too much time on that because I need to move forward. I want to thank you very much for listening. Please do the homework. It's not hard. See you in class.